Thank you. So yes, hi everyone, I'm going to talk to you about wavefront sensing control using a pixel in the science detector image. So today each telescope are equipped with or will be designed with adaptive optics. So it aims at correcting a wavefront that is distorted from a point source like a star due to atmospheric perturbation. But as you can see, the light that goes into the camera is not sensed by the AO system. And so there are still some residual that goes into the camera that we call the non-common path aberration. And so you understand that it's a necessity to find a way to use the light received from the camera to the fine-tuning for residual corrections. So how can we use an image as a wavefront sensor? So actually, we need to break the degeneracy of the aberrations. So for example, here this is a symmetric pupil. If we add an aberration that is even with a positive sign and a negative sign, you can see that the intensity received by the detector is the same for both cases. So the image is degenerate and there is a non-simple solution for this case. However, if we use an asymmetric mask, we can see that there is a bit more light here in the bottom center, and for the other case, it's in the top center. At the same time, if we use a symmetric pupil with adding a defocus, we have a scattering light that is on a diagonal on the opposite side for each of these cases. So for both cases here, the degeneracy is lifted. So we can use the image as a wavefront sensor. After that, we need to use a we can use a excuse me. We can use a regular step for a wavefront sensor. So we need to build a response matrix R that can be do by using a calibration basis, a Fourier basis. So we input sinusoidal shape on the DM. We record the modified image due to this DM shape. And we subtract this image with the reference image. So we save the differential data cube, the differential image data cube here. And if we vectorize this data cube, we have the response matrix R. So here there is the example of reconstruction that we get with these methods. So the first column here corresponds to the input aberration. So on the top, this is an astigmatism, and on the bottom, this is for different number of modes that we have used for constructing our basis. And this is the residual error. So this is the solution between the reconstructed wavefront and the input that we have. So see as it moves that the quality of the reconstruction changes, but for both cases, we can still identify the aberration that we have made, that we have inputted. So the quality changes. This is due to the fact. So we have is not square. Sorry. So we have to. This is the equation here. So S corresponds to the singular value plot, and U and V transports correspond to the basis, to an orthonormal basis of the singular values. So this is the plot of the singular value in logarithmic scale here in y-axis, and in x-axis this is the index of the modes that we have used. Sorry. So the question here is how many modes should we keep? Because if we don't keep any modes, we are going to lose signal. But if we keep too much singular values, we are going to induce noise in our matrix because the latest singular values are small. And so here, this is a simulation result that I can present to you. So the idea is to input an aberration. So here, this is a vertical astigmatism, for example. I've used an asymmetric pupil, and here, what is plotted for different amplitude of aberration. So in y-axis, this is the reconstruction that we have as a function of the theoretical RMS that we should get from this input. And here, the blue things that are moving correspond to the number of modes that we have kept to build our invert matrix. So if everything was perfect, all the blue dots should be aligned with the red curves, but you can see that as it moves, the curves become more or less linear. So to conclude for this method, we can say that it is usable for a wide range of aberrations. Here I only presented to you the Zernike mode, but you can do that with other aberrations. It seems that we have a linearity domain between minus 50 to plus 50 nanometers. And the reconstruction fidelity of the image is a function of the number of modes SVD that we are keeping. And there is currently a sensitivity study with Skexeo in Hawaii that is planned. Thank you. If you have any questions.
Thank you so much, Coline. That was great. I don't see any questions yet, but I certainly have a question. Forgive me if you said this. We had a small connection issue there for a second. Did you say how many pixels in your science image that you were using? And do you use the full image? Do you select certain pixels? And if you do, what metric do you use?
Yes, so I've cropped my image. So I have a 62 radius image actually when I'm doing this. This is at the size to be at least a Nyquist template, and I've cropped the image to avoid having some noise due to region that will not be corrected by the DM that we are using. And the DM that has been used, the simulated DM that have been used for this simulation has 2,500 actuators.
Okay, thank you. And then we have another question from Steven Boss, who wants to know if you have tried your algorithms with any different types of pupil plane asymmetries.
Yes, I did this experience with another asymmetrical mask. The result was almost the same, and I've also worked with defocus, and we find the same tendance. We get approximately the same result with some maybe sometimes a bit more signal or less signal if the asymmetry of the pupil is more if the pupil is more masked or not. But we find the same thing for other configuration of pupil.
Okay, thank you. And then we have another question here from Tasir, and I'm sorry if I get people's names mispronounced. The question is it normal to see this asymmetry in the linearity curves for plus and minus a positive excitation on the DM?
Sorry, I don't understand the question. Can you...
So let's see. So I think the question is how does this asymmetry affect the linearity regime that you're showing here in your simulation results?
Oh, it should not affect the linearity domain. What the asymmetry actually does is allows to recover all the aberrations. So actually, if we didn't have an asymmetry, we will not be able to recover the sign of the aberrations. So the asymmetry is just here to break this degeneracy, as I showed in the beginning, but it does not affect the domain of linearity. I would say maybe, but I'm not sure to say something right. But I would say that the more we mask the pupil, this is obvious that the less we have a signal. But so this is maybe one thing that can affect the linearity domain. If we have less signal, we maybe are not able to correct at high aberration amplitudes. But otherwise, the asymmetry does not affect the linearity domain.
Great, thank you. I'm sure that Steven Boss and I will have further questions for you later on. Very interesting work. Thank you so much. Really appreciate it.